So we're starting lecture 20 right now. So this lecture, what it will deal with is we are going to talk about the continuation of discussion on Henderson Hasselbalch equation, okay, and its application on the amino acid side chain properties. So Henderson Hasselbalch equation and its role on amino acid side chain properties. Okay, so last class we left the class in this point. That is, we took an example of aspartic acid. So this is aspartic acid right here. Okay, this has three different pKs. This is the pK of 1.88. This acidic group side chain has a pK of 3.7, and amino group has a pK of 9.68. As we mentioned, when these groups ionize, that is, ionization means H plus forming H plus and A minus. That is, this group will form CO minus and H plus. Okay, this will form NH2 plus H plus, and this will form CO minus and H plus. So when these groups ionize, depends on the pH of the solution. Okay, so that is defined with the Henderson equation. Then what we did, we calculated the ionization ratio. So this is acid 1, that is COOH, alpha COOH, which is this. Then this is acid 2, which is side chain COOH. And this is acid 3, that is NH3 plus. So what is the ionization ratio, meaning A minus by AH for different pHs? So you can see pH 1.5, these are the ionization ratio, pH 3 these are the ionization ratio, pH 4 these are the ionization ratio, and so on. So we also learn to summarize the whole thing, that if the pH of the solution is less than pK, the ionization or percent ionization would be less than 50%, right? If the pH equals to pK, the percent ionization would become 50%. If the pH is more than pK, the percent ionization is over 50%. Okay, so that is something we calculated in the last class, and we will be we proved that using Henderson Hasselbalch equation calculation. Okay, one more very important point we just started discussing is the charge of the amino acid. So when the pH is 1.5, okay, this first acid group, when the pH is 1.5, none of the acid group is dissociating above 50%. So all of them has very low dissociation. When the pH is 3, it just crosses the pK of this group. Okay, so this one has a over 50% ionization, but the other two is still less than 50%. Meaning that this group here, the COH group, this releases its proton and it becomes minus charge. But the others are still as it is. So this is COH and this is NH3 plus, right? So net charge of this molecule is neutral. Whereas pH 1.5, the net charge is plus 1. You can see how that is. So this is only the amino group having the net charge. Similarly, at pH 4, the acid group 1 crosses 50% ionization. Acid group 2 also crosses 50% ionization. So, but as the NH3 is still below 50%, so this is minus charged, this is minus charged, but amino is still amino. It's an ammonium form. The net charge here is minus 1. Okay, so you can see in this particular pH range, the net charge switches from +1 to neutral to -1, right? So what we can say is that the net charge of the molecule is also a pH dependent property. Okay, so that is a statement. Net charge of the molecule is also a pH dependent property, okay, which you can predict on the predictable on the basis of the pKa of the molecule of the acid groups in the molecule. Okay, so let's get that. Okay, so then if you increase the pH, the net charge then becomes -2, right? So you can see in a pH dependent manner the net charge changes. Okay, so what is the implication of this? The implication of this is that something called isoelectric point. So isoelectric point, as we see in this case, is that in this particular pH range somewhere, the molecule becomes neutral. Okay, so isoelectric point is defined as the pH at which the amino acid is neutral. That is, the zwitterionic form is dominant. Okay, so how do we calculate the isoelectric point? So for neutral side chains, those neutral side chains means that does not have any dominant acidic or basic group. The isoelectric point is calculated by the average of the two pKs. Okay, that is the carboxylic acid and the amine. That is, carboxylic acid means the alpha COH and amine means alpha NH2. So if you just take their pKa and take an average, it would become the isoelectric point. Okay, so for example, glycine, if you take the pK their pK of this group is 2.34, side chain acidity is 9.6. So the isoelectric point is the average of the two, that is 5.97. Okay, so at 5.97, this is neutral. So let's just say that happens, but what is the proof that actually happens? That also you can calculate using Henderson's equation. Let's just do that. So I'll just copy the isoelectric pKs so that I could be able to show it. Okay, so this is being glycine's pK. Okay, sorry. And this is the isoelectric point. So we want to prove that, can you prove that isoelectric point, the solution really becomes neutral at isoelectric point pH? Okay, so what would be the way to prove it? So we would use the Henderson's equation to prove this. So Henderson equation states that pH equals to pKa plus log 10 A minus by AH, right? So let's just see what would it be for the glycine. So this is glycine, this is NH3 plus, and this is COOH. Okay, this has a pKa of 2.34, whereas this has a pKa of 9.6. So what we are going to do, when this dissociates and or ionizes, this would become CO minus plus H plus, whereas this dissociates, it's become NH2 and H plus, right? So what we will do, we will calculate the A minus by AH at the 5.97 pH for both the acid groups. Okay, let's start with the COOH group first. CO minus with the H and H plus. So for this, the CO minus by COOH would be 10 to the power pH minus pK. Okay, so we just summarize the whole thing and we just shortcut the whole thing, and we took the pK to this side and did the antilog of this, so that will be pH minus pK. So 10 to the power at pH 5.97, this would be 5.97 minus 2.34. Okay, let's see how much that is. So 10 to the power, let's see how much it is that. 5.97 minus 2.34, 3.63. 3.63. So let's just see how accurate, what exactly that number is. Okay, so we'll quickly go to the calculator. Okay, while that is loading, why don't we do it for the other one? Let's calculate it for the second group. So that is the NH3 plus equilibrating into NH2 plus H plus. So for that, this is the A minus and this is the H, right? So for this, you can see NH2 by NH3 plus, concentration would be 10 to the power pH minus pK again. So that would be 10 to the power, this pK is 9.6, so 5.97 minus 9.6. So if you calculate, that is going to be 5.97 minus 9.6. Okay, so that is going to be 3.63. 10 to the power minus 3.63. So we can rewrite this as 10 to the power 3.63 by 1, whereas we can rewrite this as 1 by 10 to the power 3.60, because this is a minus sign, I am able to take it to a denominator. So how come these things look so similar, right? It's just a bit of an inverse that is differentiating the two. Well, because we took an average of the two, right? That is why. So, but what exactly does this means? The first statement means, our first equation means, there are 10 to the power 3.63 negatively charged species. So how am I able to tell that? Because this equation tells the ratio of the negatively charged species compared to neutral species. What does the second equation tell me? This tells me that there are 10 to the power 3.63 positively charged species. Okay, so the number of negatively charged molecules or species in this at pH 5.97 is the same as number of positively charged molecules or species at pH 5.97, which overall implies that the solution is neutral. Right? The solution is neutral, which is the definition of the isoelectric point. Okay, so that is what we are seeing. So this is how you can mathematically prove that at this isoelectric point, the solution becomes overall neutral. Let's see what it means for acidic side chains. For acidic side chains, the isoelectric point is calculated on the basis of the average of the acidic side chain. So meaning that this is aspartic acid. So aspartic acids, acidic side chain 1, the alpha COOH has a pK of 1.88, whereas this side chain has a pK of 3.65. So the rule suggests that it is the average of these two, that is 2.77. So we want to verify if that is true. So does the solution really become neutral at isoelectric point again? Isoelectric point pH. Okay, so we want to do it again using Henderson equation. Okay, so we will do it in the next slide, but let me just copy this thing. So this I want to copy. Okay. So we are proving that at this particular pH, the solution is truly becoming neutral. Okay, we have copied the two pH values. Let's look at the structure of the aspartic acid. So aspartic acid, there is this NH2, NH3 plus. Okay, which has so we'll come back to its pK, COOH. This is CH2COOH. Okay, and this is H, so this is 1.88 pK, this is 3.65 pK, and this would be in the range of somewhere 9.68. Okay, this is 9.68. Okay, so that is the pH. So again, what we are doing a long calculation on the base to find out the aspartic acid, the equation, aspartic acid dissociation ratios. So we start with Henderson's equation again. pH equals to pK log 10 A minus by AH. Okay, let's start with this group, that is alpha COOH dissociating into alpha CO minus plus H plus. So in this case, the CO minus, this is alpha COOH, CO minus by COOH is 10 to the power pH minus pK. So that means 10 to the power, the isoelectric point being 2.77. So 2.77 minus pK is 1.88. Okay, so how much is that? So that would be 2.77 minus 1.88. Okay, 0.8 to the power to 0.89. For the side chain COOH, that is dissociating into CO minus plus H plus. So CO minus by COOH becomes 10 to the power pH minus pK equals to 10 to the power 2.77 minus 3.65, which would be Calculate that. 2.77 minus 3.65. So 10 to the power minus 0.88. Okay, and the NH3 plus would be dissociating into alpha amino, would be dissociating into NH2 plus H plus, forming, so this should be NH2 by NH3 plus, which is 10 to the power pH minus pKa equals 10 to the power 2.77 minus 9.68, forming 10. See how much that is. 0.77 minus 9.68, that is minus 6.91. Okay, so that is that. So let's see what exactly does it mean. So so this is the ratio for the alpha NH3, which is NH2 plus H plus, forming NH. The ratio of the amino by NH3 plus would be 10 to the power minus 6.91. Okay, so what I will do for the fourth one, that is this one, I will rewrite this like the following for our ease of showing it. That is NH3 plus by NH2, and that would do the same calculation, that is and it would become, this is the inverse of this one, that is 10 to the power 6.91. Okay, now if I proceed, so these are the ionization ratios. If I proceed to calculate the percent ionization of each of these ones, what would it come out? So I have done the calculation and I'll put the values directly, so you're welcome to do it yourself. So how we do the percent ionization, so that we discussed in the last lecture. So these are the percent ionizations. So the percent ionization for CO minus and COH group, it is 88.58%. For this group, it is 11.64%. For this group, let's just ignore this one. And for this group, the NH3 by plus by NH2, it is 99%. So what does it imply? It implies that 88% of the COOH would be present as negatively charged CO minus. What does this imply? It means that 11.64% of side chain COOH would be present as negatively charged CO minus. What does this imply? This implies that 99.99% of the NH3 plus will be present as positively charged NH3 plus. So if you add this to the 88.5% plus this one, it would be close to 99%, or if you add this up, it would be almost 100%. So what it means is that the total amount of negatively charged groups is the same as total amount of positively charged groups, which is this much. Meaning again, so total negatively charged groups would be same as total positively charged groups, meaning the solution would be neutral. Okay, so that proves the isoelectric point for the acidic side chain also. So you can do the same for the new basic side chain. So for the basic side chain, for example, in histidine, this is the one side chain here, and these are the alpha amino and alpha COH groups. So the isoelectric point here is the average of these two, that is pKa2, which is 6, the higher one, and this one. So the average of these two would be 7.59, and you can do the similar calculation on the ionization ratio. Similar calculation using ionization ratio and percent ionization. Ionization to prove the isoelectric point. Okay, the same way we did in the last two slides. Okay, so what is the charge of an amino acid at pH below and above its isoelectric point? So the point I'm trying to make in this particular slide has a lot of general implication. So let's find out. So this pH, this is aspartic acid again. So this pH is 1.5. So its isoelectric point is 2.77. We figured out in the last few slides. Okay. So this pH, it is below its isoelectric point, below Pi, below Pi. This is close to its isoelectric point, and this is above its isoelectric point. Okay, and if you do the chemical equation, chemical structure of this one, so when it is pH is below its pK, and you can do those calculations again. So net charge would be plus 1. Okay, at isoelectric point the net charge is neutral, and above isoelectric point the net charge would be minus 1. Okay, so you can use this in a general statement that positive when the pH is below isoelectric point, and negative when the pH is above its isoelectric point. And the important point here is that this statement is true for proteins and peptides and other materials also. So it is positive below its isoelectric point, and this is negative when it is above its isoelectric point. Okay, so please do remember this. It's a very important point when you are doing material science or consideration of a protein state in a particular pH. Okay, so this particular one is a chart of isoelectric point calculation. Okay, borrowed from internet, of course. So this you can verify what we just learned. That is how aspartic acid, glutamic acid. These are alkaline side chains, lysine, histidine, and arginine. And these are acidic side chains. Okay, how the isoelectric point can be calculated using the side chain pK and the alpha amino and alpha acidic groups. So what is the use of isoelectric point in everyday bio? Okay, so we can use it to explain how milk is a suspension. So milk is composed of predominantly the protein casein. Okay, so you need to first Google the pH of the milk and find out that what is the pH of the milk. So it's gonna be around 6 to 7, but I'll let you find out what precisely it is. Then find the isoelectric point of the milk casein. Then you have to find out the charge of the milk at its pH. So remember, again, when the pH is below its isoelectric point, the protein is positive. When the pH is above its isoelectric point, the protein is negative, or the solution is negative. Okay, so if you use that, you will be able to find the charge of the milk at its natural pH. When you decrease the pH, that is, increase the acidity of the milk, would it make it neutral? What do you think? So now, when the pH becomes reaches the isoelectric point, and the suspension becomes neutral, would the proteins still be in suspension? Okay, so can you use this point to understand how the milk is a suspension at its natural pH, and then you can expect what would happen when it reaches the isoelectric point. You can use this to explain how milk coagulates when it is added with citric acid from lemon. Okay, you can use it to correlate your observation from the last semester on the buffer capacity experiments of the milk, where milk was added with HCl, and you see at some point after it crosses its buffer capacity, the milk starts to coagulate. It still requires heat, but you will be able to see some coagulation even without the use of a heat. Okay, so try to explain this and we can discuss this further in the class. Okay, so I'm going to stop this video at this point and we'll move on to isomers in the next class.